welcome back from coffee break. Another hour and 15 till lunch, which we will be herded through very gracefully by Raquel Queiroz, who joins us from Columbia University. Big congrats to her. But I'm mostly excited about this talk because it's our first real chalk talk. Thank you. It's been a very long time since I've seen a talk. It's been a very long time since I've seen a talk. That's what's saying with the microphone. Yes, that's right. Without further ado, I'll give it to you, and I'll give you a warning when you're all set.
Thank you so much. And thank you all for being here. It's really great to be here in person. And like you said, the first short talk. So if anything is not clear, you can see for mainly people out there, it's not becoming enough. Just like a little bigger. So the school is about flat bands and hidden correlations. I'll completely forget about correlations and only talk about flat bands. And not even talk about flat bands, talk about electrical bands in general. Because if you think about a flat band, what do you have? Like, you don't have an effective mass. You don't have effective velocity. You don't have any of these things that classically you can compute all of the transport properties of the system. So what is left is really the wave functions, right? So this is all we have, and it becomes extremely important to talk about how these wave functions look like, what is their structure in momentum space, and so on. And really, the quintessential example of a flat band is the polygon, where you have momentum. It's only here for show. You basically have a bunch of Landau levels where the Hamiltonian is just a projector into the wave functions of this band. The Hamiltonian, like the energies, are basically zero for the or whatever is the level, the energy of the Landau level. And we know that they're characterized by some number, and that we learn, Chern number, which is the Chern number, Chern number 1, Chern number. Actually, everyone has Chern number equals 1, because the total Chern number will be how many you're actually filling. And we know that some very specific transport properties, like the Hall conductance, are directly going to be related to this Chern number. Right? So the Hall conductivity is going to be where this quantity here, which is the very curvature, can be computed simply from the wave functions. So that's depending on the band. Where this is the very connection. Okay, so if, this is a total derivative of some vector potential, which is not something that is taken very into this, it's just a quantity that you would have depending on the actual structure of the wave functions. And it seems to be a kind of an unreasonable thing to write, right? You write this operator, and somehow you have a number that has something to do with the transport. So for me, it is very, very useful to think about these quantities in real space, because I understand my world is in real space. I understand real space much better. So if I see here something which is a derivative of momentum, I know what this is in real space. It's position. It's just a Fourier transform of position. So you see that when we have these bands, besides all of the properties which are dictated as symmetry operators, there's some very important contribution which has to do with how position how the position operator behaves in the space of the band, so projected into the space of the band. So this guy, if I would integrate it, so if I would integrate this over the Brillouin zone, okay, which is basically taking the expectation value of the position operator in a given band. It's basically a phase that tells you where the states are. It's about the states where they are within the itself. So this is called the very phase, or also the Z phase. And one thing that so if we want to understand how this actual transport how this type of conductivity affects actual transport of electrons, we know that if we open boundaries, you will have a certain number, C number of edge modes which go around it. So this is really the building block. This expectation value of X is really the building block that we are missing when we're trying to describe various eigens, like block eigenstates. We can talk about symmetries, but we also need, very importantly, to remember that if we are in a periodic lattice, we also care about where these electrons are in the lattice, besides, so where these electrons are in the lattice. Okay, so what I'm going to do, and of course, today I'm not going to talk about topological bands. I'm not going to talk about bands that have a nature number. I'm only going to talk about atomic bands, which are very boring type of flat bands. You know, you have a flat band. You can think about flat bands in two limits. In one sense, you can think about something which is atomic. It's kind of a frozen world, right? Where all of the electrons are perfectly localized in one position. They don't talk with each other. It's basically a quantum dot limits, and all of the physics happens actually in 0 dimensions. If we have a band that has now a Chern number and this kind of flat bands, the flatness comes from some kind of like quantum interference, and there will be a little bit more structure in there. And we're going to listen to a lot of talks I think during this summer school about these types of bands. And I'll try to then on the next talk, where I'm going to focus on topological bands, and so as opposed to atomic bands, I'll focus on like response properties rather than too much about how these bands can be constructed, which I think is going to be covered in the next talk that I'm doing. So my first talk is going to be atomic bands. And second talk is going to be topological bands. So we're going to do basically slowly the SSH chain, and then eventually go back to that two-dimensional analog of the SSH chain. So if we have just imagine we started the type binding model. We started the lattice. All matter is constructed out of atoms that give us some orbitals, and at the end of the day, we can describe crystal matter by some type binding Hamiltonian. Which very, very generally can do like this. Here, where basically this operator, what it does, it creates a localized state in a position I with some orbital character sigma, and this tells you how much it couples to another state. So it will manipulate a position J with some orbital character W. So these states basically, which are these localized states, form a basis, or basis states, and by definition, they will, in order to be faithful bases, it's really nice to think about Gaussian real space also because of all the symmetries I included almost by definition, right? So we build everything from the bottom up from our basis states. These need to be some set of states which are symmetric. So what it means is that there should be some operators, which are some symmetry group operators of the space group of your system, and maybe additionally to some local symmetries like spin rotation symmetry or whatever you would like to think about. So these states should be symmetric under sigma. These states should be symmetric under all of the symmetries that leave that point invariant. So all the symmetries of that particular lattice plate, and this is what's called the side symmetry group. It's a smaller group than the total space group. So if you think about the square lattice, all of the lattice will include, for example, translation symmetry, which of course doesn't leave every point invariant. So on one point, you will have mirror symmetry, you will have C4 symmetry, and so on. But of course, these are not eigenstates of my system. The eigenstates of my system are going to be loss states. Because we have usually translation symmetry in our system. So this means that there's this operator and the Hamiltonian will have some eigenstates, which have some energies. There's going to be also some translations, and there's some lattice vectors R. And some additional space group symmetries, which transform under some representation. Okay, so let me explain here the indices. So alpha designates a band, right? So this means that every state which is related by symmetry, by any operation of the space group, is going to be with the same index. And here is going to determine which state, the state that it's inside of the band. Of course, the Hamiltonian is diagonal, and we are not, if we're thinking about flat band, we don't really care about this, so n alpha equals just alpha. And they are all labeled by some momentum. So generally, you can think about this, we can look at this n and just read momentum. That would be the best way. Now, crystalline symmetries won't necessarily be diagonal, right? So if you have some states in the inversion, for example, of taking one point of the brilliance onto another point symmetrically, really by inversion. So this is not generally going to be symmetric. So and if I know, so if I forget very much about this, if I know about these two properties of the states, I almost know everything about the eigenstates of my system and I can call it a day. But the point of this talk and the point of many of the other talks that we're going to do is that no, this is not true, right? We need to know some additional information. These are symmetries. They will tell you something about a single state. You need to have more information that comes not from a single state, but from the collection of all of these states. And those are topological properties. In particular, if you want to compute the position operator, the expectation value of the position operator in a specific band, you will need to have all of the states in the brilliant zone in order to compute that. But in the flat band limit, I think in the atomic case, in the flat band limit, knowing this information, and this information really determines your complete properties of your eigenstates. So that is it. So okay. I wanted to also say, please interrupt me to make this a little bit more dynamic. Yes.
Can you explain again what the index tau was?
The tau?
Yeah.
So that was just some orbital character. So here I'm considering how a symmetry element of the space group at some state, and that can not make the state invariant, can just make it to a different state. But if I'm thinking about the specific orbital character, it needs to be that orbital, that state, so the local state, my basis state, right, needs to transform under some, so it's in some position, and it needs to transform under certain kind of orbital. There's some certain way under the symmetries that leave that point invariant, right? So one thing that I can imagine, and I'll just do that exactly now, is you can think about these states to be in, for example, an s orbital or a p orbital, and in that case, the sigma will be different So for example, the inversion under this state S, I'll get positive, right? The character of the inversion of an S orbital is 1, and it's +1. It's even under inversion symmetry. And the p orbital will be odd under inversion symmetry. And you can see that, right? Usually when you draw like that an S orbital, so draw a p orbital which has different phase on each of the lobes. If I invert it, I'm going to get a minus sign in this case. This one is positive, this one is negative. And this is the way that you actually distinguish between different orbitals. So it depends on the group that leaves this site invariant, what are the different orbitals that I can have, and those are called the irreducible representations of this site. So we can think about a very simple example, and most of the time here we're going to do simple examples. So imagine I do have a chain, unit cells, and I have reflection symmetry. So if I take this site, for example, in the lattice, I can reflect under the site. I call this site I. Okay. So if I'm off to put one orbital there, this orbital is required to respect the symmetry. So I can do that either put an S, or I'm going to put a P, or I'm going to put a D, or whatever it is that respects the symmetry. Now, I could choose equally another mirror center or reflection center in every single unit cell, right? There's plenty of them because the space group, it's really generated by this one of these mirrors and by translation symmetries as well. Right? So these are the elements that generate the group. So this means that I can also have another mirror inversion center here and another one here. And just by translation, I must make sure that this orbital is repeated, right, everywhere, and so on. Now, there's another one, and this is actually where topology starts playing a role, which is, imagine I combine mirror with translation. So I'm going to do it here. Imagine I start with this point, I mirror to here, and then I translate it by one unit cell. That will bring me here. So what I've done is that I mirrored, I can construct another reflection center that takes me this point directly to this one. But that reflection center is going to be here in between. Okay? So it happens all of the time in crystal lattices that there's many inequivalent points that have the exact same symmetry. So we call these points, so this mirror here will be a combination of Luna and in translation. So there's two distinct points, which I'm going to call 1A, and I'm going to call 1B, and I should maybe call this guy 1B and this 1A, which are inequivalent points, because you cannot get from one to the other with a translation symmetry, but they are equivalent in the sense that they have the exact same symmetry, and you could populate either this one or this one. These are the labels for the weakest positions of the symmetry group. And of course, you can immediately see that they share something different, and that different is the position, the actual position. So this guy has the position of it is 2.5, because it's on the edge of the unit cell, and this guy is 0 because it's on the center of the unit cell. So that's a very simple way. Now, what is very important is that if you are to have one electron in this lattice, and now if you choose to populate this site, and if you choose to populate this site, these are actually two distinct systems, in the sense that you could never go from one to the other smoothly. That sounds like topology, right? So that is exactly what happens. And you can see it very clearly that you cannot. So basically, if you put, let's say, an S orbital in the position 1A, it's different and put in a s orbital. I'm going to keep it as this now. S orbital with position 1b. And you can see this very clearly because you see that they will transform rather differently from all the symmetries in the system. So if I write a projector 1a as the sum of my sites, or my basis states, which are just going to be a bunch of s orbitals on here, and so on. And if I write my projector into 1b, which is going to be exactly the same, just in 1b. These two projectors, they span different spaces. And we can see that, and basically what we're going to try to do is how to quantify how they span different spaces. Is there a question?
Can you explain again why S in 1A is different than S in 1B?
So this is exactly what I'm going to try to justify to you. So I'm just saying this as a statement.
Oh, okay.
These two are different. What do I mean by different is that there's no smooth connection between one and another. I could not possibly, so I can quantify that by writing a projector, which defines the space of where the cell lives and where the cell lives. And what they're saying is there's no smooth connection between the two. There's no unitary transformation that will take this space into this space. And that would mean that if you were to do that, you run into trouble by closing the gap.
Professor, can you clarify where is the A side or B side in your video?
So I chose A to be the center of the unit cell and the B to be the edge of the unit cell. I put here 1. This 1 generally means that it appears, it's a site that appears once in the unit cell. I could have chosen a different type of site that exists also in this group, which is like, for example, this and this together. This is a 2, I'm going to call it C. It appears twice in the unit cell. And why is that? Because this guy, I itself, is not reflection symmetric. So if I would reflect, I would get here. So they only together, they really form something that is a very integral symmetry. So now I want to justify to you that these two guys are distinct. Right? These two. And well, we have a lot of space. I'll just keep on erasing, I'm sorry. So what I can do is I can just show you how the representations of the symmetries work for these particular configurations. So I'm going to consider a very simple, very small chain where I have maybe a little bit more. So if I write how this chain of electrons is represented, so how beer is represented in this chain of electrons, let me say that, in the position space, that's Ij, which I'm going to write the full matrix here. This is a very big matrix where I will have here a +1, which means that is this guy that is invariant under reflection itself, so it's an s orbital, so you get an s plus. There's periodic boundary conditions, so I'm basically identifying this guy with this guy, right, the ends of the chain. So I will also have another +1 here, and everybody else is going to be mapped into one another. So I will have a bunch of zeros, and I'm not keeping the dimension here, and this is how it's going to be represented in the space. If I take the trace, which is a basis independent quantity of this operator, I'm going to have 2, because nothing of this matters really, and only those 2 chains. So another way you can see this guy, why this guy is symmetric, of course, it maps into itself, but you can put this on a ring, right? And you have this point and this point, which are symmetric. Now, if I were to put these atoms on the edges of the unit cell, right? There. These electrons localizing the edges of the unit cell. Then it's going to be quite different. So the representation, so this is 1A, the representation for 1B. Every single electron is going to be mapped into another. So the way that you represent that, 0 is here, 1, 1, 1, 1, 1, 1. So if you calculate the trace of this matrix, which is the character, you're going to have 0. So just from this bare statement that you have, yes.
Here, are you able to mean have an even number of unit cells? If you have an odd number in the top in an array, then you don't have that.
Right. That is a very, very good question. So there's always, so if I fix the number of sites of unit cells, I will have always the distinction between the two. The trace is actually going to change. Right? So if we are, and I'll go now to momentum space in a minute, where we actually think about having an infinite chain. And then this question doesn't become, it's not so important anymore, but it's basically whether you get k equals pi or don't get k equals pi, right? So this two, that's the difference. But that comes always with the fact that you have a finite chain. But the difference is real, right? There's this guy different than this guy. This is basis independent, which means that this operator could never be transformed into this operator with any infinite. And this is really basically enough, but we continue just for the sake of making things little. And we go to momentum space, which I think it's also quite important to understand. And I think that Leslie probably alluded to this type of construction before in her talk. Which is, imagine now that instead of looking at these localized side states, which are these phi's, I look at the block states, right, which are the eigenstates of my system. It makes way more sense to look at those states. And if I look at that, I could, how do I construct block states out of this? It's basically a superposition of them, and I'll give them some phases, right? So I can write, I'm not going to write all of the states because we have a finite time, but it also doesn't matter. But I can look for a k equals 0 and k equals 5. So this will be adding an e to the I k dot r, so k equals 0, so the same phase at every single site. So this will basically be whatever is my wave eigenfunctions, looks like that, it repeats periodically, and I will have the same phase everywhere. You can very clearly see that if I reflect, this is an eigenstate of inversion with a positive sign. If I look at k equals pi, then of course this guy here is pi, means that I get the minus sign every time I translate. So I get this type of configuration. So my eigenstates are going to be extended, and they're going to have an alternating phase. And you can see also very clearly that if you invert that, you get the exact same thing. So this state also is even under inversion. Now, in the second case, in the second scenario, which was this was 1A, this was 1B, the second scenario, my electron charge is located away from this period. So I can look at k equals 0, you can look at k equals pi again, and if I invert this one, I'll get positive. And if I invert this one, I'll get the phase of minus. So if I were to compute the trace of the representation here, of course the representation is in, we're expressing it in the momentum basis. The 1A will have one bunch of zeros. zeros and ones, things that don't enter to the trace. And in the 1B, okay, prime, I would get +1 on the k equals 0, and I get -1 on the k equals 5. So if I take the trace here, this guy is going to give me 2, again, independent of the bases that I'm looking at, obviously, and this guy is going to be giving me 0. So this is a way, so it's basically what it tells you is something that is basically the first step in symmetry indicators. Just looking at the symmetries of a specific set of states, you can already tell information about where the position of the atoms are. In particular, what is the expectation value of the position operator, or what is the Zatrace? So you can just look at 0 and pi. And in the 1A case, you would have plus plus, and in the 1B case, you would have plus minus. And so the group of Andre worked out all of these for you, and this is all tabulated right in the Bilbao server, and that is kind of like the basis of topological quantum chemistry, which basically is telling you that by knowing how the states, atomic states, transform under certain symmetries, like mirror symmetries, and additional information about vary phases, you can actually label all of the atomic bands, and you can then compare your bands, your specific set of bands that your interest with this high symmetry point representations, which actually what they are is in the momentum basis, the diagonal entries, and only on the high symmetry points. So usually that goes by the name of band representation. But now I think a word of caution here, and you might notice immediately, is that it really depended on the unit cell that I chose. Right? If I shift everything, then all of this change. So it happens many times for all atomic bands, and the whole distinction between atomic bands, they're really relative distinctions. I can only talk about this guy in comparison to this guy, and not on its own, because I would have to need physical information about what is the unit cell in order to tell anything about some distinct physical response. Right? So this is enough for us to tell that these two spaces are not connected to each other. So generally, and then again, I'm going to introduce here an operator which is not really used, but I want to put it here. Maybe at some point it will be written somewhere. It's a bit inspired in a paper by Vanderbilt from 2006, and the overlap matrix, which is the overlap operator. That should tell you something about whether or not the two spaces can be connected to each other. So if I have some state, or basically what are states which are connected, let's say I choose a band, I choose this band by alpha. And every single state that is connected adiabatically to it, there should be some parameter, smooth parameter lambda, that acts on your initial state, that at some point at lambda equals 1, you should recover your states. And what is really important is that this guy needs to be smooth and periodic in the Brillouin zone. So all of these concepts of topology actually just make sense in the limit that I take n to infinity in order to define what this smooth actually means. But it's very important to be periodic, because imagine that I have let's say this is labeling K on the position on the 1B, on the states of the 1B versus the 1A. So the states in the 1B look a little bit like that. We'll just put it explicitly later on. And the 1A, which are in the center of the unit cell, as if they are not momentum dependent at all, I could think about acting with this U matrix, right? With this U operator, which is labeled here K, prime, and so on. I could move them. But if I don't make sure that this guy is smooth and periodic, then I could easily just swap all of them up. But if I make sure that it's smooth and periodic, I'll have a problem in the South Pole, and these two can never possibly be connected into one another. So the two spaces, they're unitarily equivalent. This is satisfied. And if this is satisfied, it also means that all of the representations of all of the symmetries would also be unitarily equivalent. And of course, these are really big matrices. And if I want to look at just some specific diagonal elements, I should write this guy here in momentum basis as I'm going to write it only with one index because it's basically the diagonal entries. So if I find a matrix valued function U that satisfies this for all of the symmetry operators, then I am in a very good shape thinking that the spaces are inequivalent, they cannot be reached to each other. So the quick and dirty way of looking at that, it's by computing this overlap operator, which I'm going to define it here. Which you might, it's not. It's basically what we're doing is that projecting one space into the other and seeing how many states do we have left. And if two things are related to each other that are dividedly connected, then we make sure that the rank of the first band, so the number of states that we have in the band, must be the same as the number of states that we have in the other band we're getting to, and that the overlap still has the same number of states. If I don't have that, right, then I lost some state, and I'll get this operator be singular, which will actually have quite a bit of consequences, and we'll try to discuss those consequences later on. So this you can look at in real space basis. You can look at in momentum space basis, whatever you would like. But basically, if we have in any basis you were to choose, the determinant is going to be, because it's a positive definite matrix, this guy is going to be smaller than whatever is the trace of the product of the diagonal matrix. So let me say it here. So in particular, because I do have, in my two cases, I know that my pi state in 1A is going to be orthogonal to my pi state in 1B. And why this is guaranteed? Because if I were to put here and dagger, I'm going to get a minus sign in one and a positive sign in the other. So this is going to vanish. And this is like why every time you have things transforming under different symmetries, they're orthogonal. So that if you have these orthogonal states, then we necessarily have this guy to be singular. Okay. So basically what I'm doing is a projection, right? I pick up this state and put it on top, and I see whether the states are orthogonal or not. And if they're orthogonal, I'm going to have a determinant 0. So if it is if they're topologically distinct, I know this is going to happen. If they are not topologically distinct, I can have multiple zeros in the eigensets of this operator. And so, like, you know, it could be that this almost wraps, but it doesn't really wrap. So you're going to miss sometimes those cases. So that's why it's a quick dirty. It does give you false positives, so good antigen test. Is there any questions? Okay, so the model where you can have this 1A and 1B as your ground states, everybody knows is the SSH name. How am I doing that?
You got about 15 more.
Okay, so I need to hurry up. Okay, very good. So the SSH chain, of course, I have a bunch of atoms. I have a strong bond and a weak bond, and a strong bond and a weak bond. And if I look at the band structure, it would look like this if I don't have any difference between T1 and T2. And if I do have a difference, I'm going to open up here at the Berlin zone edges. So the symmetry, the inversion symmetry of this point equals 0 is fixed, it's always plus. And if I choose S orbitals, but here I can choose, I get a pair of pluses and minuses, so that I can put the plus down and the minus up, or vice versa, I could put the minus down and the plus up. So those two configurations, now you know, we find out immediately that these two pluses looks like 1A, and this plus minus looks like 1B. We, of course, to be completely honest, we would need to calculate the actual value centers, the actual expectation value of, because we expect this guy to be 0, we expect this guy to be 1/2, but we would need to actually calculate it. And the way that you calculate it, that you compute the value centers, the value functions out of the block states. Those are defined in this way. Some arbitrary phase. This arbitrary phase lets you change a little bit the form of the Vanier centers, which are localized states, but in particular in atomic bands, because there's always going to be a way of making this guy extremely sharp, and so sharp that they will get to the perfect on initial localized states. This is because, why is this true? Is because really like it's a property of the block functions that they don't really have irremovable singularities. They're still periodic, depending, choosing the right center. We will need to choose the right center, but then we will be able to do that. And you can calculate it. I mean, the two atomic limits, we basically have an Hamiltonian being T1, and the other one is T1, T2 into the IK, T2 into the IK, and we are welcome to just punctuate to the very base and find out that they have. But really, I want to keep our conversation completely in terms of real space and just what we expect. And now we're going to physical observables. So this is in an actual system, you would have the center of the unit cell, you would have a positive charge. So the two different situations, choosing the centers of the unit cell or the edges of the unit cell, would correspond to put the cloud of the the negative charge either on top of the positive charge or in between.
Okay.
Yes?
So why we need now a localized basis? Why you choose to work with Vanier and not a block?
Because I really like so the going to that phase is basically going to flat band limit. And I really don't care too much about the energies in this system. I'm trying to just show what what are the topological content of these numbers? It doesn't really matter. So if I were to look at the Wannier function, that would be bigger. The center is gauge independent, so the center is really what matters. If you were to completely localize it, you can localize it exactly on the Wannier center. Now, Wannier functions are not gauge invariant themselves. There's really no good meaning to choosing any of them, so might as well choose something which is completely localized. Okay.
But this is a general statement. When you have a flat band, you prefer maybe to work with Wannier than a block, because Wannier is more localized?
Yes. So I think that in general, if we're talking, what flat bands brings us is that, the fact that brings us is that perfectly localized states become eigenstates of the Hamiltonian as well, right? Because you can choose any linear combination, so you might as well choose something local. When you have flat bands, you're really welcome to choose to look into a completely localized state. And if you have something which is atomic, then this is the only considerations. If you have something which is not atomic and you can get to the flat band very quickly with quantum Hall effect, you actually have some constraints. So you can localize, you can still talk about things in a rather localized manner, and we're going to do that, and there's going to be more talks about it, but you cannot localize them perfectly. Right? You cannot possibly localize them perfectly, and we'll get there. So instead, we just talk about physical observables here. So there is a bulk quantity that is different from this case and this case, and this is the bulk polarization. Because here you have net zero polarization at every single unit cell. In this guy, you have a half polarization, so basically E polarization per unit cell. And these two you can of course measure directly by looking into the bulk, but it also matters. It also has the consequence when you open boundaries. Okay, so if you now consider opening the boundaries by making this chain finite, and we do some counting, here if we have, okay, we have 4 plus, so we have, and we should put on top 4 electrons in order, 4 minuses in order to get charge neutrality. So I can put them right on top. No problem. Okay, so I have no problem preserving charge neutrality and preserving the symmetry of the system. No problem whatsoever in this particular case. Now here I have a problem because symmetrically I could put 5 of these, but I only have 4 electrons. So I really have to choose, right? I will have to choose to put either on this side or on this side. So I am required to break the symmetry in order to preserve charge neutrality. And there you can see that there's going to be an excess of negative charge on this side and an excess of positive charge on this side. So the fact that you have a bulk polarization is translated to the edge, and you have a net edge polarization. So this is what's called a filling anomaly. And this name was coined in this PRB. And Vladimir Nalkazar, which is here in Princeton, so you can talk with me. And there's, of course, many other communities that talk about this a bit in a slightly different manner, but the point is that you really have a problem when you're trying to fill inner states. And you're going to have charge quantization because of that. And that is quite nice. The way that you can see in terms of symmetries is that imagine that you lose a bunch of inversion centers, right? You lose all of the inversion centers except one, which is the one right in the center of the chain. And the difference between this guy and this guy is that either the center is filled or is not filled. So in an atomic band, what atomic band means is that I can represent all of my symmetries in a completely local manner, right? In acting on local states. Now I have something a bit different, because once I reduce the symmetry from periodic boundary conditions to open boundary conditions, the symmetry representation with respect to this mirror remains exactly the same in the first case, so still local. But in this case, it's not anymore, because it maps this set into this set. So there's no local representation of this for mirror symmetry on this guy. So this really, the representation of the mirror with respect to the origin is going to be different with open boundary conditions than with periodic boundary conditions. That always happens for these types of certain cases. So what happened is that a site that was the edge site that had a multiplicity 1 under the symmetries became a site of multiplicity 2. You changed the multiplicity, but you didn't change the filling, so now you have to half fill, and half fill is complicated. So you need to break this. But that actually gives you a hint on why, we talk about orthogonal space, but why are these technique gap states? Why are they even inside of the gap? Yes?
In the Millian anomaly, why does it choose an edge? If you chose the center state, you still preserve the symmetry.
So right. So there's 2 degenerate states. There must be 2 degenerate states, one in each site. Why you would do one or the other is just local breaking of the symmetry. In the end of the day, the electron will choose.
Yeah.
The electron will not be fractionalized.
Yeah, but if you leave the center state vacant, create the mirror plane, then you would break the mirror symmetry.
So you would break. So that's how you would do it. Eventually you break the symmetry a little bit, and you would utilize that to choose one of the states to be occupied. And that state will by construction of the symmetry. So that basically tells you. So basically with open boundaries. So in this SMH case, you have a filled band and an empty band, right? With open boundaries, in order to guarantee all of the symmetry constraints, I have to have 2 degenerate states, which I have to fill just one. I only have one electron to fill, right? And that's how they need to be at 0 energy to have chiral symmetry, and that's how you guarantee that these states need to be inside of the gap of the system. Okay, so I do have time to go through. So let's do that. Now another model, and this model kept me awake at night, I must say, that Vladimir also introduced, is the called BPH model, which is the science. Basically, it's a 2-dimensional model where you have a bunch of sites. The unit cell is 4 by 4. It's not really it's like a 2-dimensional version of the SSH, where you have strong bond, weak bond, strong bond, weak bond, strong. And I try to not, okay, I will make a mistake, but just put the bonds in the right places. And in order to gap all of the surfaces of this system, this is the unit cell, so it's a 4-band model. And in order to gap out all of the boundary states that you will have a bunch, because this is a bunch of SSH ones, you put a pi flux through the middle. So this really tells you about something about the local representation that you choose. So here you go to an S orbital or P orbital, you choose actually a 2-dimensional orbital, which I'm going to call P, because that's the actual name for it, which is a representation, or E bar, which is a representation that guarantees that there are 2 reflections in X and Y antikinute with each other. How can you see that? You can imagine going around this plaquette here. So you can do that by mirroring under this mirror, then mirroring here, and mirroring back. So you circle this plaquette, you pick up a phase of minus, so they guarantee that these 2 operators and units. So the field states, the 2 field states, there's like 2 bands. These field states, you can construct localized orbitals for them. They're going to be two states, but they're going to pin to each other because they're the same representation. This is a 2-dimensional 2D representation. So you can think about it PXPY or something, but it's not really good. So you can choose a specific basis. So then you would have mirroring X, S, I can call the matrix X, mirroring Y, you might call the matrix Z. And the representation of mx and y is just -1. So this could be very similar to the SSH chain if I would have an additional symmetry, and that would be C4. If I have C4, I would be forced to pin those two states right on top of each other, and I could choose them to be either on the center of the unit cell or the edge of the unit cell, and we could do the exact same story that would have two states. But it's not. This was not there, and that's why it kept me awake at night. Because there's going to be a filling anomaly in this model, even without the C4. How you can see it is that there are these two weaker positions. There, if I were to tile, I would have exactly the same number of them if I have periodic boundary conditions. But if I open the boundary conditions, I don't anymore, right? So basically we have the exact same reduction of the multiplicity. So so if I, if this is just square lattice, I can choose the charges to be here, or the charges to be here. The number of O's equals to the number of X's with periodic boundary conditions, obviously, because that's just a shift of 1/2 in the diagonal. But if I open the boundaries, you can see that I have more of one than the other. In particular, the corner here, which was identified as a single site, becomes 4. And I have two field states, so I'm going to have a problem. If I'll compute the spectrum of this guy without any C4 symmetry, and I'm going to forget everything about Hamiltonians. This is great. I have 4 states here in the middle, and I'm going to fill 2. And I'm going to, so it's going to be, I'm going to fill these states in the corners. I can put excess of negative charge here, or I can put negative charge there or there. I can choose my way. But what I will have no polarization, but I will have a quadrupole moment. And this quantized quadrupole moment appears because of this filling anomaly. But, and now let's maybe utilize all of that machinery that I talked about unitaries for so much time, so I better use that a little bit. Oh, okay, I deleted the, sorry. Okay, so we had the representation. Let me remember that the representation of y of each of these states were sigma z if they were localized in the center, in the 1A position. But it could also be sigma z e to the I kx, ky, kx, if they were localized somewhere else, like in the 1B position. How do you see that? Again, drawing lattice. If I'm here and I act to the my, I go to itself. But if I'm here, if I act to the my, I come here and I need to come back and get the ik face. So these two actually tell you how the states are localized in different positions. They will carry a different value of x. Now, these two states are, so there's two states, not just one, it's this E doublet. And I could think about moving one in each direction. It's completely symmetric, right? I can move this guy here, keep this symmetry, and I keep this symmetry. I could do something else even, which is just rotate x and y. And then these two states which are a bit deviated in this direction, they would be just deviated in the other direction. It's just a basis change, right? So I could easily move them from here to here. So if I were to do that, you can imagine moving them around and really bringing them from this point all the way to this point. And you can just do it, no problem. And I can write you exactly what is the unitary transformation that does it. So that will take you from position 1A to position 1B for mirror in Y and then mirror in X or I might be making a typo here, sorry, but you can do that for every single one. You're always going to find a unitary matrix, which means that the projector of the 1A is equivalent to the projector of 1B.
Okay, I have a quick question.
Yeah.
With inversion, right, with the X times NY, the 1A and 1B positions are distinct high symmetry points, right?
Mhm.
So how can you bring states from both 1A and the
They are not, but the trace is going to be 0. They're not, so they're going to be, okay, it's going to be -1 on both, and it's through all of these different positions, always going to be -1. So it's not there, you cannot distinguish them by symmetry eigenvalues. And all of the others have trace equals 0.
And so this because they form like a reducible.
They form together in a reducible representation, but it's movable.
Yeah, I see. Okay.
Yeah, exactly. But they have, so basically they're the same because there's a unitary transformation that will take one to the other. Now, of course, if I open the boundaries, if I actually decide on a boundary, I will have to choose which inversion center is preserved and whether it is filled or not. So there's still the filling anomaly remains, I guess, like the only reason that so this is actually one case, which is this now I'll finish here, which is when B periodic boundary condition. So once I reduce the symmetry, the representations from one way and 1D that were the same, isomorphic to one another, they become not isomorphic with one another once I chose the boundary. So the topological obstruction only exists with open boundaries. So this is what we call the boundary obstructed topological phases. And yeah, it's a little bit strange, but it is exactly what it is. So I hope I managed to convince you at least that even thinking about topological abstractions in the most simple atomic bands, it's still interesting to think about it. And on the next lecture, we'll talk about topological bands that you cannot think about a single position anymore. Thank you so much for your attention.
We have still like 2 minutes for questions.
Oh.
So we run now and get the microphone. Sure.
Can you comment on differences between these boundary obstructed topological phases and the ones that we're kind of used to thinking about in terms of what happens when you add interactions or what you might be able to experimentally in terms of differences, that kind of thing?
Right. So the difference is that there's only disconnected sectors. So you only require to close the gap from going from one to the other to make states within these spaces. If you have open boundaries, this means that you can tune from one to the other by closing the boundary gap and not the bulk gap. So in terms of interactions, all of these phases are kind of boring, okay? Because, like I said, all of these states are exponentially localized and can be made completely like orthogonal to the state next door. So in order to interact, we'll have a little bit of a problem. You can interact with some long-range interactions, but then you create some bandwidth. So this is all pretty frozen and interesting in the interacting phase, as far as I know. So maybe there is something to say. So I must say I didn't say this, but once the charges, if we know this physical information of where are the positions of my atomic positions, and the electrons are not on them in a way, there's a name for this, which is obstructed atomic movement. Which was this is a concept that was introduced into PC. So this means that, okay, you can construct perfectly localized states, but those localized states are not going to be on your original site. The way that we can think about them is that it's like a bonding or an anti-bonding type of state. We have least both here and here. So there is a little bit of an overlap that is hidden in there. And that can maybe lead to some interesting non-interacting physics. And all I talked about here so what I talked about here, boundary obstructions versus bulk obstructions, this is for the bulk. These are kind of like details of where the things are exactly. I don't think there's a major difference between them.
So what's the consequence with this interpretation of the local?
What's the consequence here?
Yeah, so
So for example, in this particular model, you have a quantized edge charge or corner charge and quadrupole moment in a total sample. So if you look at the open boundary system, you'll have to choose where you put these charges. And then you'll have some too much negative charge on this direction, too much positive charge on this direction, so you have an actual total quadrupole moment. And these states are going to be localized on the corners. So the way that what I said before, that you basically will have in-gap states, right? You'll have these two field in-gap states, and that is because of this condition. So the fact that the two cannot be directly connected to one another, you will actually need to close the gap in order to remove these in-gap states. Now, what I am saying is that if you put periodic boundaries, you wouldn't. So you can close this gap by being just a surface gap. So these two phases, if you periodic boundary conditions, you could move them from one to the other. These ones with open boundaries you can't, and you actually have boundary states to separate them.
Jenna, we have a question.
Yeah.
On the webinar.
Yeah, okay. Yeah, just going to ask a question from one of the webinar attendees who's asking whether you can comment on the difference between the topological obstruction here and wire obstruction.
Okay, so usually when we talk about Vannier obstructions, we talk about a topological obstruction to construct a Vannier function, an exponentially localized Vannier function. This topological obstruction does not exist in any of these situations. You generally can, but you can possibly not be able to construct a Vannier function on the position you want it. So in an obstructed atomic limit, you can construct an exponentially localized Vannier function, just not on top of the the atomic site. It needs to be off it in some other symmetric center. So because again, in the crystalline systems, we have so many equivalent by symmetry centers that cannot really be deformed into one another. But when we talk, I think the term obstruction of Vannier functions, it means that I cannot construct them to start with. So if I were to try to construct them, I would start and I would try to orthogonalize them, and we'll talk about this in the next lecture. You would start getting like longer and longer and longer tails, and you end up having polynomially localized Vannier functions.
Great. So Raquel's last talk is on Friday. I think let's get for one last hand, and we'll all go to lunch.